Banded iron formations, the rock that tells the story of the oxygen revolution.
This is an excerpt from Timefulness, a book by Marcia Bjornerud. Most rock types, for example the basalts that mid-ocean ridge volcanoes exude, or sandstones composed of the granular remains of other rocks, are more or less timeless in the sense that they form on Earth today in the same way they have for billions of years. But the unimaginatively named sedimentary rocks called iron formations accumulated during only a specific interval in Earth's history and record a one-time revolution in the planet's surface chemistry in the early Proterozoic era, between about 2.5 billion and 1.8 billion years ago. In particular, these densest rocks testify to changes in the air, the transition from a surface environment with no free oxygen to a brave new world created by the rise of oxygen-emitting photosynthetic microorganisms like blue-green algae or cyanobacteria, whose modern descendants are often called, with less than due respect, pond scum. This was the Earth's third atmosphere. The iron formations, found most notably in Australia, Brazil, Finland, and the Lake Superior region, are beautiful rocks with striking color palette. Fine laminae of silver hematite and black magnetite alternate with gray chert and red jasper. They can be many hundreds of feet thick and are typically mined in giant open pits like the enormous Hull Rust Chasm, the Grand Canyon of the North in Bob Dylan's hometown of Hibbing, Minnesota. Apart from their metallic composition, the iron formations have sedimentary characteristics very similar to those of modern limestones, indicating they must have been deposited in a shallow marine environment. Yet, in today's ocean, iron is in such short supply that it is a limiting nutrient, an essential element whose scarcity holds biological productivity in check. A controversial climate engineering scheme is even based on this fact. The idea that if the oceans were fertilized with iron powder, cyanobacteria would bloom and photosynthesize enthusiastically, and, if all were to go according to plan, sink to the ocean floor, sequestering large amounts of carbon without, fingers crossed, wreaking havoc with the rest of the marine biosphere. In contrast with the trace amounts of iron in seawater today, the tremendous volume of the iron formations visualize all the steel in the world's cars, aircraft, buildings, bridges, and railroads, attest to the great abundance of iron in the Proterozoic oceans.
So let's talk about the story of banded iron formations. This timeline puts into place banded iron formations and some of the major other events in the formation of our planet. To begin with, we have our first oceans, which start when we have crust for water to collect upon. DNA is something that we are pretty certain had to occur early on in conjunction with our first oceans. However, this is something that biologists and geologists alike are still looking for concrete evidence for. Then we begin with tectonic activity after the formation of the moon, and with that comes the first continent, and sometime after that, the first prokaryotes. And at this time is where we see banded iron formations proliferate across the planet, and following that, the great oxygenation event. For this talk, we're just going to focus on the latter parts here, but it's important to see where they're situated within the early Earth events. If we take a look at a cartoon diagram that puts in more detail than the previous timeline, we can see a few important things for situating this list of major geologic and biologic events. The beginnings, we have this solar nebula, and this is 14 billion years ago. Then at 4.5 billion years ago, we have our molten Earth early Hadean phase. The part that we're interested in for this story begins after the formation of the moon, after the formation of the early Earth's crust, and here where we see banded iron formations alongside with this question of origin of life along mid-ocean ridges and the beginning of chemosynthesis, perhaps. Let's zoom in on this little section here. To begin today, this is what we're going to explore: banded iron formations and cyanobacteria. What is a banded iron formation? Well, for short, we call them BIFs. I like to remember the name BIF because for me, it reminds me of these guys in the gym who only work out their upper bodies. When I hear the word BIF, that's what I think of. But in addition to that, BIF stands for Banded Iron Formation, which is a description of what these rocks look like. In this photograph, you can see there are stripes of red, black, and white over and over and over again in this outcrop. Well, they are indeed a sedimentary rock composed of thin chert bands, which is silica, interlayered with iron oxide minerals. The iron oxide minerals can be any number of different mineralogies, from oxidized iron sedimentary rock to minerals like hematite and magnetite. Banded iron formations, we believe, have two main depositional environments: submarine volcanic zones, which are the very, very old ones for the first part of this talk, and rift basins, which are also extremely old, but slightly less old than the submarine volcanic zones. Both locations together provide necessary sources of iron and silica, and sufficient amounts to begin to understand the sheer volume of banded iron formations that cover our planet. So let's look at life in the Archean. This is this first time period after the early Earth's crust. Our earliest fossils are simple microbes, and these are preserved only as molds with carbon in Archean chert. Single-celled organisms that are just carbonified holes in Archean chert. We believe these represent cyanobacteria, or blue-green eubacteria, most of which are photosynthetic. So this means they're photosynthesizing, and photosynthesis, if you need a reminder, is the formation of food and oxygen from sunlight, water, carbon dioxide, and various mineral nutrients. Plants undergo photosynthesis still to this day, as do blue-green algae. But what's really critical is that this, at this time, would have been the first photosynthesis and the first production of oxygen. So if we look at a cartoon of what things are going on in the Earth's formation, again, in our early Earth, the Hadean time period is this time period of molten Earth. Everything is just molten. It's like an entire planet is volcanoes. Through the Archean, we still have massive amounts of volcanic activity, tons and tons of volcanic activity. The composition of the atmosphere is very different at this time. In this cartoon, you can see a few pieces of data that are being represented. Solar brightness is this top straight line, and we don't need to worry about that right now. Surface temperature, we can see gradually is decreasing into the Phanerozoic. This is, of course, in result of the crust cooling on the surface. Below that is this line of atmospheric carbon dioxide. And so atmospheric carbon dioxide was very, very, very high in the early Earth. And well below that, you can see this dashed line of atmospheric oxygen starting with 0 and moving its way up over time into 550 million years ago at the beginning of the Phanerozoic. This origin of atmospheric oxygen coincides with the origins of photosynthetic bacteria, or cyanobacteria, or blue-green algae. So this is also the time period that we're most interested in for the first phase of banded iron formations. In order to begin banded iron formation, we need the oxygen revolution, which is the beginnings of free oxygen in the atmosphere. The early atmosphere had no free oxygen, and therefore also no ozone layer. This is dramatically different from the atmosphere that we know today. And as a result, there's totally different chemical reactions that were ongoing in the past than that happen now. Our early oceans were also rich in dissolved iron and silica. These are present in extremely rare amounts today. Why is that? Well, silica today, while it's rapidly being deposited into seawater from terrestrial sources, is being consumed at the same rate it's being inputted. This silica today is being dissolved by organisms so that they can use them to make their skeletons. Diatoms consume vast amounts of silica, and these are pretty much the bottom of the marine food chain. Furthermore, iron today can only be dissolved in oxygen-poor water. Right now, that's the Red Sea, and only bacteria survive there. Why is water not oxygen-poor today? Because today we have free oxygen. And in our early atmosphere and early oceans, there was no free oxygen. So there was also no oxygen dissolved in the oceans either. If we look at a cartoon, and yes, this is a complex diagram, this is representing the formation of this iron and silica rich ocean composition. We've got active submarine volcanism. This is what's being represented here. Mid-ocean ridge volcanism, also known as moors. And then we have these oceanic basins. This is the continental margin. We've got these volcanoes that are rapidly erupting in this early ocean. And as a result of these eruptions, it's introducing tons of hydrothermal iron. Hydrothermal simply means hot water iron. And in our anoxic ocean environment, the dissolved iron can be transported and deposited. There's a lot of chemistry and a lot of words on this diagram, but the point is to illustrate that we have tons of volcanism happening underneath the oceans and inputting both iron and silica into an anoxic ocean water system. So we know that banded iron formations can be traced for hundreds of miles across the surface of the planet. These deposits are absolutely massive. We can tell from the principle of lateral continuity and the bands of sedimentary rock within the banded iron formations that these were laid down uniformly and continuously. We don't see surfaces of erosion, and we do see extremely uniform thicknesses of the bands throughout, even when they're folded. These iron-rich materials, such as hematite and magnetite, can only be formed by an oxidation reaction. And you need a very specific set of chemical conditions to undergo an oxidation reaction. Since the early atmosphere had no free oxygen, even with volcanoes outgassing, what they're outgassing when it's oxygen is not O2, it's oxygen bonded to other elements. So we have two models to demonstrate how banded iron formations could form in the early ocean in these specific conditions. But as I mentioned early, neither alone can account for the sheer volume of banded iron formations worldwide. So probably both models were important in the formation of banded iron formations as we see them on Earth today. These two models are inorganic precipitation and organic precipitation. So not only are they contingent upon the certain chemical compositions of the early atmosphere and early ocean, but they're also contingent on the existence of early photosynthesizers. In the inorganic precipitation model, ultraviolet radiation forms an iron compound in surface water. That iron compound can then precipitate out. In the organic precipitation models, bacterial photosynthesis and also chemosynthesis breaks up dissolved iron carbonate to generate energy, and that too releases iron oxide that is free to precipitate out. Let's have a look at a cartoon to illustrate a little bit more of this. So here again is our ocean environment. We've got shallow carbonates, which are calcium carbonate. We've got shale, which is silicate rock. And we have banded iron formation layered down below. I'm not actually sure what the GIF, it's probably some other kind of iron formation that's not banded. So what we're looking at in this illustration is our surface water, the shallow water within the photic zone. And then we have the chemocline where we're getting into the deeper waters where there's no more light rays penetrating. And we can see our early bacterias and photosynthesizers hanging out in here. So in this environment where we have probably volcanoes, submarine off to the right, in the deeper ocean where you can see this input of iron 2. And then we've got terrestrial runoff on the left-hand side where you can see silicate as well. So we have oxygenic photosynthesis, simple photosynthesis of these photosynthesizing bacteria above the chemocline in the photic zone where they get solar radiation incoming and they photosynthesize. And in doing so, release iron oxide. We also have ferrotrophy. So below the chemocline, below the photic zone, we have chemotrophs who are doing a form of photosynthesis. It's not really photosynthesis, really. They are consuming purely chemicals and releasing iron oxide as they generate energy. And in the meanwhile, we also have ultraviolet radiation coming in from the sun, no ozone layer, mass amounts of ultraviolet radiation, hugely penetrating these surface waters. And this is number 3 over here, where in that photic zone, photooxidation takes place, and that too results in free iron free to precipitate down. So there are different kinds of iron oxide precipitates in the banded iron formations, and it's likely that all 3 of these mechanisms, the 2 organic forms and this 1 inorganic form, precipitated out iron oxides over vast expanse of time. The formation of banded iron formations and the composition of our present-day atmosphere both require the appearance of free oxygen. So cyanobacteria were critical both in the formation of these rocks and in the formation of our modern atmosphere that stopped the formation of these rocks after this point in time. So building up to the oxygen revolution, we needed cyanobacteria to create oxygen. This in turn resulted in banded iron formations forming, and with the abundance of free oxygen resulted in the chemical conditions no longer being possible to generate banded iron formations, all from these single-celled organisms photosynthesizing away. So to reiterate, with the presence of free oxygen in the oceans from our early cyanobacteria, a new niche appeared, that for iron oxidizing bacteria. So we think that the cyanobacteria and the ultraviolet radiation were both the preliminary sources to generate banded iron formations. And then after a while, a new niche was filled by iron oxidizing bacteria, providing the 3rd form of producing iron oxide sediment and the 2nd form of organic precipitation. Those cyanobacteria, they're still present today. This is a photo from Shark Bay in Australia, where cyanobacteria form these mud mounds as they have always done in shallow waters. These are just layers of photosynthesizing bacteria and silt that build up over time in these shallow, quiet waters. We see records of these guys as far back as well over 3 billion years old. And we even see banded iron formation stromatolites, which is a solid piece of observable evidence in the rock record to support that these organisms were actively depositing iron oxide sediment way, way back in geologic time. With free oxygen in the ocean and the atmosphere, another new ecological niche could be filled, that of respiration. So not only are these cyanobacteria changing the atmosphere, changing the rock record, they are actively changing biology. And as free oxygen built up in the atmosphere, ultraviolet radiation actually produced the ozone layer, which consequently now blocks most UV radiation. So think through that transformation in atmospheric composition over time. No free oxygen, tons of UV radiation. UV radiation triggering chemical reactions in the shallow oceans, early bacteria emitting free oxygen, UV radiation interacting with that free oxygen and zapping O2s into O3s, which consequently form a layer high above the stratosphere that blocks out UV radiation, that in addition forms another barrier to the precipitation of banded iron formations. It's just an amazing sequence of events all around this single element. In addition to banded iron formations, there are a couple of other oxygenated rock types that are also highly reliant on there not being free oxygen and on there being high amounts of volcanism. Uraninite is a rock type that is rich in uranium and is not found in rocks younger than 2,300 million years. And by 1800 million years, BIFs also become extremely rare in the rock record. Uranium oxide is the primary mineral in these banded uranium formations. And of course, you have oxygenated iron. Similarly, we have sedimentary copper deposits that show up around 1700 million years ago, and then they no longer appear after that. And these sedimentary copper deposits are also copper oxides. We look at a not very appealing figure to demonstrate this change. On the left-hand side, on the y-axis, we have atmospheric oxygen. You can see it caps out at 20%, which is where we are today, and it begins down at 0. And then the time x-axis starts at 4.5 billion years ago and moves up to present day. So for the first 3.5 billion years of Earth's history, of course, the first 500 million years, there was no rock. But after we had rock, there was no photosynthesis whatsoever. Then 3.5 billion years ago, we see the first evidence of oxidized iron in rock, which indicates that there must have been free oxygen, which indicates there must have been photosynthesis. Then for the next several billion years, all free oxygen that was being emitted is being reabsorbed in the ocean or by seabed rock. So the water is dissolving oxygen into it, and iron oxide, uranium oxide, copper oxide are precipitating that oxide out in the form of metal oxide deposits. Eventually, the output of oxygen is so high that that threshold is crossed, that it can no longer be absorbed into the ocean, and because of other chemical environment conditions, those metals can no longer be dissolved into the ocean water. Imagine the sheer volume of oxygen that had to be produced by photosynthesizing bacteria to complete this transformation. This threshold, this increase from 0 to 20 is incredibly rapid, geologically speaking. And this threshold is crossed right around 550 million years ago. So what happens then? This is where we have the earliest animal fossils. But we're not going to talk about that today, because today we're talking about banded iron formations. So let's move into the second phase of banded iron formation deposition, the old as opposed to really old deposits. You can see at the beginning of the Proterozoic era, we have this peak in banded iron formations, and then it starts to taper out. And this coincides with glacial episodes as well, the mega glacial episodes, the snowball Earth episodes. And we believe these things are tied together. So I like to call this section BIFs in rifts, because it rhymes almost. By about 3.5 billion years ago, photosynthetic prokaryotes began releasing oxygen to the atmosphere and ocean, as I mentioned. And most banded iron formations were deposited between 3.6 and 1.9 billion years ago, in conjunction with this free oxygen emission by cyanobacteria. But we see a few Neoproterozoic and Phanerozoic examples of banded iron formations that are rare and relatively small in size compared to the early Archean and Paleoproterozoic examples. So how did these ones form when there was significantly more free oxygen in the atmosphere? Well, the best example we can use is from the Amazon craton. During the Neoproterozoic or late Proterozoic, the Amazon craton started to rift apart. This is what we call a failed rift. There's an example of one of these in the Lake Superior region of North America, and another one that's a modern failed rift today in the Red Sea area in East Africa. So a failed rift forms a typical 120-degree triple junction, a Y shape. And this is where the continent starts to pull apart, but doesn't actually make its way all the way down to oceanic crust. So at the same time as the Amazon craton was starting to rift and failing, it was also completely covered in ice. So in this rift, we have active volcanism that is diverging apart, splitting apart, and it is capped with ice, which is a pretty good lid. And inside we have water because it's we've got a source of water above and a source of heat below. So in the middle, we're going to get water. And what are the volcanoes outputting? Sulfur, carbon dioxide, silica, iron, other metals. So the volcanoes are outputting all kinds of elements and acids that are going to result in a near anoxic water environment that is absolutely loaded with iron and that is capped by this ice cap that prevents it from interacting with the atmosphere. So these volcanic outputtings are going to be ongoing for the duration of the Snowball Earth episode and super saturate these small zones of rift basins with volcanic material and no additional oxygen. So in these small rift basins over time, we end up generating a newer version and a smaller version of what the early Earth's atmosphere and oceanic systems would have been like, making these small, isolated, banded iron formations in glaciated rifts, or BIFs in rifts. To finish off, let's just have a look at a map to show you this Amazon craton and the 120-degree angle Y shape that I mentioned, so you can visualize the shape a little bit better. And might as well zoom in and take a look at the sheer quantity of banded iron formations present in that Amazon craton. So there you have it, banded iron formations and the oxygen revolution.